In July 2024, a massive landslide struck the Chilcotin River in British Columbia, creating a natural dam that would soon have devastating effects on the surrounding areas. What began as a seemingly routine geological shift quickly escalated into a major crisis as the landslide blocked the river, causing water to pool behind the debris, forming a temporary lake. As the water levels began to rise, engineers and local authorities were faced with the critical task of preventing a breach that could lead to catastrophic flooding downstream. By August 5, 2024, the pressure from the accumulating water became too much, and the natural dam breached, leading to significant flooding along the Chilcotin and Fraser Rivers. The flooding posed a severe risk to residents, prompting evacuations and an emergency response effort. From an engineering standpoint, the event provided real-time insights into the challenges of managing natural dams and landslide-induced flood risks. In this update, we'll examine the engineering response to the Chilcotin landslide, the tools and strategies used to prevent further damage, and the long-term solutions being considered to manage similar risks in the future. Understanding why this landslide occurred requires a look at the geotechnical conditions of the region. The Chilcotin River runs through mountainous terrain that is known for being geologically active. The area has a history of landslides, especially in regions with loose, steep slopes and high moisture content. In this case, the landslide was triggered by a combination of seasonal rainfall and natural erosion. The debris from the landslide quickly blocked the river, creating a natural dam. As the river water backed up behind the debris, it formed a lake that grew in size and posed a serious risk of breaching. Engineers have long known that such landslides can cause significant disruptions, but the speed with which the natural dam formed left little time for preparation. The environmental impact of such an event is considerable. The sudden creation of a lake can alter the local ecosystem, affecting both aquatic and terrestrial habitats. The water's high sediment content can also reduce water quality, making it more difficult to manage the river's flow in the future. Initial response. Once the landslide blocked the river, the first priority for engineers was to assess the size of the dam and its potential for breaching. Using satellite imagery, drones, and hydrological sensors, engineers were able to get real-time data about the water levels behind the debris and track its progress. Early data revealed that the water was rising at an alarming rate. Engineers began working closely with local authorities and hydrologists to develop a plan for managing the water flow and preventing the dam from collapsing. The area around the dam was rapidly monitored using inclinometers and piezometers, which measure soil and water pressure, allowing engineers to track the stability of the natural dam and anticipate potential weaknesses. Flood risk mitigation. Given the rapid rise in water levels, the next step was to plan for the controlled release of water. If the dam were to breach suddenly, the resulting flood would devastate communities downstream. Engineers used real-time data from the monitoring systems to calculate the optimal release rate, designing a plan that would ease the pressure on the natural dam while preventing downstream flooding. Engineers also focused on evacuation routes and emergency measures to ensure that residents downstream were safely relocated ahead of any potential flooding. In collaboration with local governments, flood-prone areas were marked, and emergency warnings were broadcast to ensure that residents had sufficient time to move to higher ground. Managing the natural dam. One of the most challenging aspects of this response was managing a natural dam that was unpredictable and constantly shifting. With no human-made infrastructure to stabilize the dam, engineers relied on a combination of manual assessments and technology to monitor the debris flow. The plan was to prevent the dam from breaching by ensuring controlled releases of water, while keeping an eye on any possible signs of structural weakness. On August 5, 2024, the natural dam breached, releasing a significant amount of water downstream. The breach was caused by the accumulation of water behind the debris, which eventually overwhelmed the debris' ability to hold back the water. Engineers had prepared for this possibility, and flood control measures were put into place to manage the flow of water after the breach. The immediate engineering challenge was to ensure that the water flowed in a controlled manner without causing widespread flooding downstream. Water flow control. To manage the breach, engineers utilized a series of temporary flood barriers and diversion channels to help direct the water safely away from critical infrastructure. The immediate priority was to protect communities, bridges, and transportation routes along the Chilcotin and Fraser Rivers. Real-time data from monitoring systems helped engineers make quick adjustments to their water flow management strategy. They continued to work closely with emergency responders to ensure that the release of water did not cause further damage to surrounding areas. While the immediate threat of the landslide and breach has been managed, engineers are now focusing on long-term flood risk management. The creation of a natural dam shows just how fragile the balance between human development and natural forces can be, and engineers are working to put measures in place to prevent such events from causing catastrophic damage in the future. Assessing and reinforcing infrastructure. Engineers are assessing the damage to infrastructure caused by the flooding and planning for the restoration and reinforcement of roads, bridges, and utility lines. This includes improving sediment management in areas where future landslides are a risk, and reinforcing flood control infrastructure to better handle potential future flooding. Improving landslide and flood prediction systems. The key lesson from this event is the importance of predictive monitoring. Engineers are now looking into upgrading early warning systems and improving landslide prediction technology. Advanced machine learning algorithms and hydrological models can help predict future landslides with greater accuracy, allowing engineers to prepare more effectively and mitigate damage ahead of time. Sustainable flood management. In the longer term, engineers are exploring ways to integrate sustainable flood management practices, such as reforestation and improved land use planning in regions prone to landslides. By strengthening the surrounding environment, the risks posed by future natural dams can be minimized. As this event demonstrated, modern engineering relies heavily on technology to manage natural disasters. The use of satellite imagery, drones, real-time data collection, and predictive modeling has revolutionized how engineers handle landslides and floods. Predictive engineering models. Engineers are now using artificial intelligence and machine learning to develop predictive models that can forecast landslide events, allowing for earlier intervention and more effective response strategies. These technologies help anticipate potential weaknesses in natural systems, giving engineers the ability to manage risks more proactively. Climate change and adaptation. As climate change continues to influence weather patterns, engineers must adapt their flood and landslide risk management strategies. Increased rainfall and shifting seasonal patterns can lead to more frequent and intense landslide events, requiring ongoing innovation in flood control systems and infrastructure design. The Chilcotin landslide highlights the direct impact natural disasters have on local communities and ecosystems. Thousands of people were affected by the flooding, and while evacuation efforts helped save lives, the economic impact has been significant. Impact on local communities. The flooding displaced many people from their homes and caused substantial damage to agriculture, which is a key industry in the area. Engineers are working alongside government officials to provide recovery resources and ensure that resilient infrastructure is rebuilt to better withstand future disasters. Environmental impact. The flooding and subsequent landslide also affected the local ecosystem, particularly water quality and aquatic life in the Chilcotin River. Engineers are working to restore affected habitats and improve river management systems to ensure that the area recovers from the environmental toll of the disaster. The Chilcotin River landslide event has provided valuable insights into the engineering challenges of managing natural dams, landslides, and flood risks. The rapid response by engineers to manage the water flow, protect communities, and prevent further damage has shown the importance of real-time monitoring and advanced flood control techniques. The key takeaway is that predictive engineering, combined with sustainable land use practices and cutting-edge technology, will be essential in mitigating the risks posed by future natural disasters like landslides and flooding. As engineers, we must continue to innovate and adapt to the changing landscape, ensuring that communities remain safe and resilient in the face of nature's unpredictable forces.